In a previous video, we talked about several forms of Bloch theorem in one dimension. So, for example, we figured out that if we have a certain periodic structure, then it's possible to construct solutions such that if you look at the fields at a certain position z, and you compare that to the field one lattice vector away, that the price you pay for that is simply a multiplication by a phase vector exponential minus j kza. So that's the first form of Bloch's theorem that we derived in a previous video. The question is, can we extend this to 3 dimensions, to periodicity in 3 different dimensions? And then the thing is, you can follow exactly the same argument as we did before, just focus on a single lattice vector in a certain direction in 3D space, and then you can write that, for example, the field at position r plus capital R, where r is just one of the lattice vectors that we have, will be equal to exponential minus j, and then we have k r h of r. So this is simply an extension to a different coordinate system, a different direction. Just like before, people used the Bloch vector k as a label to label the modes, and then sometimes you will see things like h sub index k to indicate that this is a certain Bloch solution corresponding to the Bloch vector k that we had there. Right, so this was the first form of Bloch's theorem, but remember we also had a second form of Bloch's theorem that in one dimension read that you can construct solutions h of z, Bloch modes, that are pseudo-periodic. Basically they consist of a plane wave exponential minus j kzz, and then this plane wave modulates a periodic function u of z, which has the same periodicity of the lattice. So u of z plus an integer number times L is the same as u of z. Can we extend this to multiple dimensions, to 3 dimensions? Well, we can do just like before. We can just focus on a single lattice vector r, which points somewhere in a 3-dimensional space. And then we can follow exactly the same argument to write down something that we can construct our Bloch modes as being h of r. Again, the product of a plane wave. If you then extend that to multiple dimensions or to an arbitrary direction, that becomes exponential minus j k r, like so. And then we have another function u of r, where u of r again is periodic with this lattice vector a that we were focusing on. So just u of r plus, sorry, I keep getting distracted by the 1D case, u of r plus L times an integer, so an integer multiple of the lattice vector we're studying, equal to u of r. So again, that's just the same reasoning as we followed earlier. It's just that rather than having just one coordinate z direction, we make it a bit more general, such that the coordinate can be, such that the lattice vector can point anywhere in 3D space. One thing that's missing in this argument, and that would be rather fun to have, is that now we focused here on a single lattice vector. Obviously, for a 3D crystal, for example, we will have 3 independent directions, and we can write down something similar for example, another lattice vector and yet another. But one thing that would be cool to have is showing that this periodic function u actually will be periodic for all of these 3 different directions. And at the moment, we haven't really shown that. We just have shown that for each direction, it's possible to write down something like this, where it's just periodic for the lattice vector that we are considering at the moment. So it would be cool to extend this such that u would be periodic in all directions. And that's indeed something very interesting to look at. However, we're still missing a piece of this puzzle in order to be able to show that. And that's something that we will be tackling in the next video. And this machinery will be very useful, not only for this second form of Bloch's theorem, but it will also come in handy when we're trying to extend the concept of the Brillouin zone, for example, to 3 dimensions. So see you all in the next video.